What if everything you've ever experienced, every sunrise, every conversation, every moment of joy or sorrow, has already happened an infinite number of times before? That's the startling claim at the heart of the cosmic loop theory, the idea that our universe isn't just expanding or evolving but caught in an endless cycle of repetition. Picture this: the Big Bang wasn't a one-time event but the latest in a series of cosmic resets, a moment when space, time, and matter were reborn, only to play out the same story over and over again. It's a concept that challenges everything we think we know about reality, and yet some of the brightest minds in physics are taking it seriously. The evidence might be hiding in plain sight. Tiny echoes in the cosmic microwave background, the faint afterglow of the Big Bang, could be scars from a previous universe. The way galaxies cluster in vast, repeating patterns might not be random but the signature of a cycle older than time itself. Even the laws of physics, the rules that govern how stars burn and planets form, might not be set in stone, just echoes of a universe that's lived and died before. This isn't science fiction, it's a hypothesis with mathematical weight, one that could rewrite our place in the cosmos. So why does this idea grip us so deeply? Maybe it's the eerie familiarity of déjà vu, the haunting sense that we've lived this moment before, or the way ancient myths and modern science both whisper of cycles, destruction, and rebirth woven into the fabric of existence. Whatever the reason, the cosmic loop theory forces us to confront a breathtaking possibility. That history isn't just written in the stars but etched into the very bones of reality, replaying like a record we can't stop. In this video, we'll unravel the threads of this mystery, from the cutting-edge math that supports it to the mind-bending implications of living in a universe that never truly ends, just repeats. Buckle up, we're diving into one of the strangest ideas physics has ever dreamed up. For centuries, we've pictured the Big Bang as the ultimate beginning, a single, explosive moment when time, space, and matter burst into existence. But what if that story is incomplete? Cutting-edge physics suggests our universe might not have sprung from nothingness just once, but could be trapped in an endless loop of expansion and rebirth. Think of it like a cosmic heartbeat. The universe expands until gravity pulls it back, collapsing everything into an ultra-dense speck before bouncing outward again in a new Big Bang. This Big Bounce theory turns the traditional narrative on its head, replacing a one-time creation with an infinite cycle of death and renewal. Remarkably, this idea isn't just modern speculation, it's a thread woven through human history. Ancient Hindu texts describe time as a wheel, with universes rising and falling through epochs called yugas, each lasting billions of years. The Greeks imagined the phoenix, a universe consumed by fire only to rise again. Even indigenous cultures speak of worlds destroyed and remade in endless succession. It's as if our ancestors glimpsed a truth that science is only now beginning to quantify. The real shock: modern equations support it. When physicists peer into the moments before the Big Bang, they find hints that our universe might have been born from the collapse of a previous one. Quantum gravity theories suggest that at extremely high energies, the fabric of spacetime could behave like a spring, resisting total collapse and rebounding instead. And if dark energy, the mysterious force accelerating our universe's expansion, weakens over time, gravity might eventually win, pulling everything back to start the cycle anew. The evidence is tentative, but the math is compelling. We could be living in just one chapter of an epic without end. What does this mean for us? If the cosmic loop is real, every star, every planet, every life form might be destined to repeat not just once but infinitely. Your laughter, your heartbreaks, every choice you've ever made could be echoing across eternity. It's a dizzying thought, one that blurs the line between science and philosophy. Are we scripting our own destiny, or simply retracing steps laid down in a universe much older than we ever imagined? Einstein's theory of general relativity didn't just reshape our understanding of gravity, it cracked open the door to a universe far stranger than anyone had imagined. At its heart, the equations revealed something extraordinary. Space itself could bend, twist, or even fold back on itself like a cosmic Möbius strip. One of the most mind-bending solutions to these equations is the idea of a closed universe, a cosmos where space isn't infinite and flat but curves gently inward like the surface of a gigantic four-dimensional sphere. In this scenario, if you could travel far enough in one direction past galaxies, past the edge of the observable universe, you'd eventually loop back to where you started, like an ant walking in a perfect circle around a globe. This isn't just speculation, it's mathematically inevitable under certain conditions. Einstein's equations show that the shape of the universe depends on a critical balance between its density and the expansion rate. If there's enough matter and energy to overcome the outward push of the Big Bang, gravity wins, pulling space into a closed geometry. Picture a balloon inflating and then deflating, except instead of air, it's space-time itself contracting until it's poised for another explosive rebirth. Some models even suggest this curvature could be so subtle that we haven't detected it yet, hiding in the faint patterns of ancient light from the early universe. But here's where it gets wilder. A closed universe doesn't just loop space, it loops time. If the cosmos collapses back into a big crunch, some theories suggest the collapse could trigger a new Big Bang, stitching the end of one cycle directly to the beginning of the next. It's as if the universe is a cosmic Ouroboros forever eating its own tail. Even our everyday intuition about straight lines would be an illusion. Launch a probe on what seems like an endless path, and it might someday return from the opposite direction, having circumnavigated the entirety of existence. So why haven't we proven this yet? The challenge is scale. Detecting the curvature of space-time across billions of light-years is like trying to sense the Earth's roundness by staring at the horizon in your backyard. But subtle clues might be hiding in the cosmic microwave background, the faint afterglow of the Big Bang, where unusual patterns could hint at a universe that's folded back on itself. And if we're truly living in a closed cosmos, it wouldn't just reshape our understanding of space, it'd mean the cosmic loop isn't just a theory but the very architecture of reality. Every star, every atom, every moment might be riding the curve of a universe that has no true edges, only endless returns. The cosmic microwave background isn't just a snapshot of the universe's infancy, it's a palimpsest, a faded text where older stories might still linger beneath the surface. Stretched across the sky in every direction, this faint glow carries subtle anomalies that defy conventional explanations. One of the most tantalizing is the so-called cold spot, a region of space chillingly colder than its surroundings by a fraction of a degree. At first glance, it might seem like a cosmic hiccup, but dig deeper, and the implications become staggering. Some researchers propose this anomaly isn't random noise, but a bruise, a gravitational imprint left by a collision with another universe, or even a relic from a cycle that predates our own. Think of it like finding a fossil in your backyard. The cold spot's unusual temperature distribution aligns eerily with simulations of what might happen if two universes brushed against each other in a higher dimensional space. Even more provocative are the large-scale patterns in the CMB that appear oddly aligned, as if the universe has a hidden grain or texture. These asymmetries, dismissed as statistical flukes by some, could be the fingerprints of a prior cosmic epoch. Imagine tossing a stone into a pond, then draining it and refilling it. The ripples from the first throw might still distort the surface of the new water in ways that seem inexplicable unless you knew the full history. The math behind this is as elegant as it is unsettling. If our universe is trapped in an endless cycle of expansion and contraction, the violent death of a previous iteration could have left scars in the quantum foam scars that stretched into the fabric of our own newborn cosmos. These irregularities wouldn't fade, they'd freeze into the CMB during recombination, the moment roughly 380,000 years after the Big Bang when light first broke free from the grip of matter. What we're seeing might not just be the afterglow of creation, but the shadow of something far older. Of course, skepticism is healthy. Mainstream cosmology offers alternative explanations for these anomalies, from instrumental errors to the quirks of cosmic inflation. But the persistence of these patterns and their stubborn refusal to fit neatly into standard models keeps the door open for more radical interpretations. If the cosmic loop theory is correct, the CMB isn't just a relic, it's a message in a bottle washed ashore from a universe we can't remember. And decoding it could rewrite not just our past but our future, a future that might already have happened infinite times before. Black holes aren't just cosmic vacuum cleaners, they might be the ultimate recycling centers of the universe. At first glance, these gravitational monsters seem like one-way streets, swallowing everything that crosses their event horizon, from stars to light itself. But here's the twist: quantum physics insists that information, the fundamental blueprint of what falls in, can't just vanish. This clash between gravity and quantum mechanics, known as the information paradox, has been keeping physicists awake for decades. Stephen Hawking's groundbreaking work suggested black holes slowly leak energy, evaporating over eons through what we now call Hawking radiation. But if that radiation carries no information, the paradox remains: where does the data go? Enter the cosmic loop. If the universe truly cycles through endless expansions and contractions, the answer might lie in the very fabric of space-time. Some theorists propose that information swallowed by black holes isn't destroyed but encoded, imprinted onto the fabric of the universe itself. When a black hole evaporates, this data could be released back into the cosmos, like a message in a bottle tossed into the future. In a cyclical universe, that information might not vanish but instead resurface in the next iteration, woven into the newborn universe's initial conditions. Picture a library where every book swallowed by a black hole isn't burned but archived, waiting to be shelved anew when the cosmic cycle resets. This idea isn't just philosophical sleight of hand, it's backed by cutting-edge math. String theory, for instance, suggests black holes might transform swallowed particles into holographic projections on their event horizons, preserving information in a scrambled two-dimensional code. If true, this data could survive the universe's collapse and re-emerge in the next Big Bang, like a cosmic game of telephone where the message gets passed through eternity. Even Hawking revised his stance late in life, conceding that black holes might not be the ultimate erasers we once feared. But how would this actually work? Imagine a star collapsing into a black hole. According to loop cosmology, the star's quantum information isn't lost, just compressed and redistributed, like a file compressed to its smallest possible size before being uploaded to a cosmic cloud. When the universe contracts and rebounds, that data could decompress, seeding the next cycle with echoes of the past. The implications are staggering. Every thought, every atom, every law of physics might carry traces of a universe that came before. Skeptics argue this stretches the limits of plausibility, but the math holds an eerie allure. If black holes aren't endpoints but waystations in an infinite loop, the information paradox transforms from a crisis into a clue, a hint that the universe has a memory, and we're living in just one page of its endless diary. Whether this theory withstands future tests or not, it forces us to grapple with a profound possibility. Even in the darkest corners of space, nothing is ever truly lost. Just waiting. Quantum entanglement might seem like science fiction, but it's one of the most rigorously tested phenomena in physics, and it could hold the key to understanding the cosmic loop. Picture two particles born from the same event, separated by billions of light years, yet still mysteriously linked. Change the spin of one, and the other instantly adjusts, no matter the distance. Einstein famously dismissed this as spooky action at a distance, but experiments have proven it's real. Now, imagine this entanglement isn't just a quirk of our universe, but a thread stitching together multiple cycles of existence. If the cosmic loop theory is correct, entanglement could be more than a fleeting connection. It might be a relic. When particles interact, their quantum states become intertwined, creating correlations that defy classical physics. Some theorists suggest these entangled states don't fully reset with each Big Bang. Instead, they leave faint imprints like shadows cast from one universe to the next. Think of it as a cosmic game of telephone where whispers from a prior cycle subtly influence the next. The universe wouldn't just repeat, it would remember. This idea gains traction when you consider quantum vacuum fluctuations, tiny, unpredictable shifts in energy that pervade empty space. These fluctuations might seem random, but what if they're echoes? In a cyclical universe, the quantum foam of one epoch could imprint itself onto the next, preserving subtle patterns in the entanglement of particles. It's like shaking a snow globe and watching the flakes settle in eerily similar patterns each time. The math even suggests that under certain conditions, quantum information could survive a cosmic collapse, tunneling through the Big Crunch like a message slipped under the door of a new reality. Skeptics argue this stretches the limits of plausibility, but consider the alternative. If entanglement is truly universal, why wouldn't it transcend a single cycle? The fabric of reality might be woven with threads that don't just span space but time, connecting universes like pages in a book. Even if we can't yet detect these ghostly links, their potential existence challenges us to rethink what it means for a universe to end. Maybe destruction isn't oblivion, just a transformation, with quantum whispers carrying forward into the next act. And here's the kicker. If particles retain even a trace of their past entanglements across cycles, it could mean the laws of physics aren't arbitrary. They might be the result of accumulated quantum memory, shaped by endless repetitions until they reach the stable, finely tuned values we observe today. The universe wouldn't just be repeating, it would be learning, refining itself with each iteration. That's a humbling thought, one that blurs the line between physics and philosophy, leaving us to wonder, are we riding the wake of a cosmic echo, or is the universe itself remembering its way home? Time isn't the straight arrow we imagine. It might be more like a Möbius strip, twisting back on itself in ways that defy intuition. Closed time-like curves, a bizarre prediction of Einstein's general relativity, suggest that under certain extreme conditions, time could loop around like a cosmic racetrack, allowing events to replay endlessly. Picture this: a spaceship follows a precise path around a spinning black hole, where space-time is warped so violently that its trajectory circles back not just in space but in time. Arrive back where you started, and you'd meet your past self boarding the ship, trapped in a paradox where cause and effect spiral into infinity. This isn't just theoretical fantasy. The equations permit it. In regions of extreme gravity, like near a rapidly rotating black hole, or in the presence of exotic matter with negative energy, spacetime could twist into a knot where the future connects directly to the past. Physicists like Kurt Gödel, who first discovered these solutions, realized they imply a universe where history isn't linear but cyclical, like a vinyl record skipping on the same groove. If such loops exist on cosmic scales, it wouldn't just mean time travel is possible, it'd mean every moment is locked in an endless rerun, playing out the same way in each cycle of the universe. The implications are dizzying. Eternal recurrence, an idea Nietzsche toyed with philosophically, could become a physical inevitability. Every joy, every tragedy, every breath you've taken would repeat identically, not just once but an infinite number of times. The chilling part, you'd never know. Without a way to perceive the loop, each cycle would feel like the first and only time. It's like rewatching a movie where the characters, unaware they're in a replay, make the same choices again and again, trapped in a script they can't deviate from. But here's where physics throws us a lifeline. Quantum mechanics might offer an escape. At microscopic scales, particles behave probabilistically, their actions not set in stone but governed by chance. If quantum randomness carries over between cosmic cycles, it could introduce tiny variations enough to break the cycle of identical repetition. Imagine a deck of cards shuffled slightly differently each time the universe reboots. The broad strokes might repeat, but the details could shift, allowing for new possibilities in each iteration. Yet the mystery deepens. Some interpretations of string theory suggest closed time-like curves might not just be rare anomalies but woven into the fabric of reality. In higher dimensional spaces, timelines could braid around each other like strands of a rope, creating knots where past and future intersect. Even our perception of time as flowing in one direction might be an illusion, a local quirk in a cosmos where time is more like a landscape with peaks and valleys we're simply traversing in a straight line. So are we prisoners of an eternal rerun, or is the universe more inventive than that? The answer might lie in the tension between relativity's deterministic loops and quantum mechanics' chaotic freedom. One thing's certain, if time can bend back on itself, then the cosmic loop isn't just a theory about space and matter. It's a story about us replaying endlessly in a universe that refuses to forget. If the universe truly cycles endlessly, why does anything coherent exist at all? That's the unsettling question at the heart of the Boltzmann brain paradox, a thought experiment that turns the cosmic loop theory inside out. Imagine a universe that's existed for eternity, where entropy, the slow unraveling of order into chaos, should have long since erased all structure. Statistically, in an infinite sea of randomness, the most likely configuration of matter isn't galaxies or planets but fleeting, self-aware fragments, disembodied brains momentarily assembled by chance, hallucinating a reality that doesn't exist. These hypothetical Boltzmann brains should outnumber organized civilizations like ours by an unimaginable margin. So why aren't we one of them? The answer might lie in the cosmic loop's unique rhythm. While an eternally recycling universe does stretch time toward infinity, each cycle isn't a blank slate. The Big Bang that birthed our cosmos wasn't a random fluctuation but a structured rebirth, carrying forward subtle imprints from prior iterations. Think of it like shaking a box of puzzle pieces. Left to pure chance, they'd almost never form a complete picture. But if each shake preserves a handful of correctly placed pieces over countless cycles, the puzzle eventually snaps into focus. Our universe's startling order, its finely tuned laws, its stable atoms, even our own existence, might not be a miraculous accident but the inevitable result of a process that's had infinite tries to get it right. Here's where the paradox twists deeper. If Boltzmann brains rely on sheer randomness, their odds plummet in a cyclical cosmos where each new cycle inherits a memory of order. Quantum entanglement, black hole information preservation, even the patterns in the cosmic microwave background, all could act as cosmic stabilizers, nudging each new universe away from chaos and toward complexity. It's as if the universe is learning, refining its own parameters with each iteration until conscious observers like us become not just possible but probable. But skepticism lingers. Some physicists argue that even in a looped cosmos, Boltzmann brains should still dominate unless there's a mechanism we haven't discovered yet that actively suppresses disorder. Others propose a spine-tingling alternative. What if we are Boltzmann brains and everything we perceive, from distant stars to our own memories, is just an elaborate illusion conjured by a random flicker of particles? The cosmic loop theory offers a way out of this hall of mirrors. If the universe has a built-in tendency toward order across cycles, then our structured reality isn't a fluke but a cosmic inevitability. The stakes couldn't be higher. If Boltzmann brains were the norm, science itself would collapse. Our observations couldn't be trusted, as even the laws of physics might be hallucinations. But if the loop theory holds, the universe isn't just repeating, it's evolving, with each cycle inching closer to conditions that favor life, thought, and meaning. It's a vision that transforms eternity from a curse of monotony into a promise. No matter how many times the cosmos collapses and reboots, the story always moves forward. And in this version of reality, we're not accidental ghosts in the machine, we're the universe's way of remembering itself. What if our universe isn't just cycling endlessly, but someone designed it that way? Simulation theory, the idea that reality might be an artificial construct running on some unfathomable computer, collides eerily with the cosmic loop. Both theories suggest repetition is baked into existence, but where the loop frames it as a natural cycle, simulation theory raises a chilling possibility. We could be living in a program set to reboot. Imagine a cosmic video game where the developers, rather than crafting infinite new levels, simply hit reset when the story ends, preserving resources by recycling the same universe over and over. Glitches in the Matrix might be hiding in plain sight. Have you ever experienced déjà vu so strong it felt like a system error? Or noticed strange repetitions in nature, the fractal branching of trees mirroring river deltas, or the way galaxies and neurons share uncannily similar structures? These could be artifacts of reused code, shortcuts in a simulation optimized to recycle patterns rather than generate true novelty. Even quantum indeterminacy, the way particles behave unpredictably until observed, fits unnervingly well with a simulation conserving processing power by only rendering reality when someone's looking. The math gets wilder. Some versions of string theory suggest our universe could be a holographic projection, with all 3D reality encoded on a distant 2D surface like a cosmic DVD playing the same film on loop. If true, black holes might not just recycle matter but data, their event horizons acting as error-correcting mechanisms that prevent the simulation from crashing when information overloads. Even the speed of light could be a built-in limit, not a law of nature but a processing speed cap ensuring the universe doesn't exceed its computational budget. But here's the twist: if we're in a simulation resetting eternally, could we ever break the cycle? Ancient mystics spoke of enlightenment as waking up from illusion, while modern physicists toy with the idea of hacking reality's source code. Perhaps consciousness itself is the wild card, the one variable that can't be perfectly replicated in each iteration, introducing enough randomness to eventually crack the system. Or maybe the simulators want us to notice. After all, what's the point of an experiment no one realizes they're in? Whether natural or engineered, the cosmic loop forces us to confront a profound question. Is repetition the universe's failure of imagination or its most ingenious design? Long before telescopes or quantum equations, humanity's oldest stories whispered of a universe that dies and rises again. The Norse spoke of Ragnarök, a cataclysmic battle where gods and monsters perish in fire and flood, only for the world to emerge fresh and green from the sea, repopulated by a handful of survivors. The Aztecs believed the sun itself was locked in a cosmic struggle, requiring human sacrifice to fuel its daily rebirth against the void. Hindu cosmology stretches even further, describing cycles of creation and destruction lasting trillions of years, each overseen by the dancing god Shiva, who dissolves reality into nothingness before spinning it anew. These aren't just tales of apocalypse, they're blueprints for a looping cosmos, etched into myth millennia before physicists put pen to paper. What's startling isn't just the consistency of these ideas across cultures separated by oceans and epochs, it's how closely they mirror cutting-edge cosmology. Take the ancient Greek concept of the Great Year, a cycle where the planets realign and history resets. Compare it to modern proposals like conformal cyclic cosmology, where the universe's expansion stretches all matter into an ultra-smooth, energy-less state, a blank slate eerily resembling the primordial chaos of Greek myth. Or consider the Aboriginal dream time, where ancestral spirits shape a world that's continually remade. It's uncannily similar to theories suggesting quantum fluctuations from a prior universe could seed structure in our own, like cosmic fingerprints pressed into newborn spacetime. Even the details align. The Mayan Popol Vuh describes successive worlds destroyed and recreated, each version refining the flaws of the last, a poetic parallel to the cosmic loop theory's suggestion that physical constants might subtly shift between cycles, optimizing the universe for complexity. The Buddhist idea of kalpas, vast epochs ending in fire or water, finds a scientific echo in proposals that vacuum decay or dark energy could trigger our universe's collapse. It's as if our ancestors glimpsed the universe's rhythm through intuition, mapping the dance of entropy and renewal long before the math caught up. But why would cultures with no contact converge on this idea? One possibility lies in the human experience of nature's cycles, day and night, seasons, generations. We're hardwired to expect renewal after decay. Yet the myths go deeper, describing not just earthly cycles but cosmic ones. The Egyptian sun god Ra sailing through the underworld each night to be reborn at dawn mirrors the trajectory of a universe collapsing into a black hole before rebounding. The Cherokee myth of the great buzzard, whose wingbeats sculpt valleys and mountains from primordial mud, resonates with inflationary theory's vision of quantum fluctuations seeding galaxy clusters. Perhaps these stories persist because they tap into a truth deeper than metaphor, a half-remembered sense that existence itself is recursive. Modern physics might frame it in terms of quantum fields and entropy, but the core revelation remains: destruction isn't an end, just a pivot in an endless dance. Whether through myth or math, we keep circling back to the same awe-inspiring possibility, that the cosmos has always known how to begin again, and we're just learning to listen. Look closely at a snowflake, a coastline, or the branching veins of a leaf, and you'll notice something uncanny, the same shapes repeating at smaller and smaller scales. This self-similarity isn't just artistry, it's the signature of fractals, patterns so deeply embedded in nature that mathematician Benoit Mandelbrot once called them the geometry of chaos. Now imagine applying that same lens to the cosmos itself. The fractal universe hypothesis suggests that reality isn't just cyclical in time. It's recursive in structure, with galaxies, star systems, and even atoms echoing the same fundamental patterns like cosmic nesting dolls. The evidence is staggering. Zoom out far enough, and the cosmic web of galaxies resembles the neural networks of a human brain, vast filaments of matter threading through voids, mirroring synapses firing across the darkness. Peer into the quantum realm, and particles behave less like tiny billiard balls and more like infinite whirlpools, their interactions echoing the gravitational dances of stars. Even the distribution of matter in the universe follows a fractal-like power law, with clusters repeating at every observable scale. It's as if the universe is a hall of mirrors, each reflection revealing the same underlying design. Mandelbrot's equations showed that fractals aren't just mathematical curiosities, they're fingerprints of systems that repeat infinitely, whether you're observing them from a mile away or under a microscope. Apply that logic to cosmology, and the implications become dizzying. If the universe is truly fractal, then our observable cosmos might be a single pixel in a much larger structure, part of a multiverse where each universe contains smaller universes ad infinitum. Black holes could be portals to these nested realities, their singularities birthing new spacetime like seeds sprouting inward. But here's the twist: a fractal cosmos wouldn't just repeat spatially, it could loop temporally too. The same forces that sculpt galaxies into spirals might govern the rhythm of cosmic death and rebirth, with each cycle unfolding at a different scale. Ancient Hindu texts envisioned this as the Brahmanda, or cosmic egg, where universes nest within universes like layers of an onion. Modern physicists like Roger Penrose have floated similar ideas, proposing that black hole singularities could tunnel into new Big Bangs, creating an endless cascade of universes, each inheriting subtle echoes of their ancestors. The philosophical weight of this idea is crushing. If reality is fractal, then free will becomes a haunting question. Are we truly making choices, or just tracing paths laid down by infinite repetitions? Artists have wrestled with this for centuries. M.C. Escher's endless staircases and Hokusai's waves within waves capture the eerie beauty of a world where every part reflects the whole. Even our search for extraterrestrial life takes on new urgency. In a fractal universe, intelligence might not be rare but inevitable, recurring like ripples in a pond. Yet the fractal hypothesis isn't without its critics. Some argue that at extremely large or small scales, the pattern would break down, smoothed out by entropy or quantum uncertainty. Others point out that while nature loves repetition, it also thrives on variation. No two snowflakes are identical, so why should universes be? But the allure remains. Whether the cosmos is truly fractal or just flirtatiously self-similar, the possibility hints at a reality far stranger than we've dared to dream. One where every atom, every galaxy, and every moment is a verse in the same never-ending poem. Dark energy isn't just some mysterious force lurking in the void, it's the invisible hand shaping the fate of everything. Discovered in the late 1990s when astronomers noticed distant galaxies speeding away from us faster than expected, this enigmatic energy makes up roughly 68% of the universe's total content. Yet despite its dominance, we still don't know what it is. What we do know is terrifying. Dark energy appears to be accelerating the expansion of the cosmos, stretching spacetime itself like taffy, pulling galaxies apart until they're lost in isolation. But here's where the cosmic loop theory flips the script. What if dark energy isn't constant? What if it weakens over time, or worse, reverses? The math reveals a spine-tingling possibility. If dark energy's repulsive force diminishes as the universe ages, gravity could finally gain the upper hand. Picture a pendulum swinging. First, the outward push of dark energy dominates, flinging galaxies apart, but as it fades, the inward pull of matter and dark matter takes over. Space would stop expanding, then reverse, collapsing everything back into a singularity, a big crunch. But in some models, that crunch doesn't end the story. Instead, it triggers a rebound, a quantum bounce where all that compressed energy erupts anew in another big bang. Suddenly, dark energy isn't just a death sentence for the cosmos, it's the engine of rebirth. Critics argue this is speculative, and they're right for now. Current observations suggest dark energy behaves like Einstein's cosmological constant, unchanging over time. But look closer and the data gets murky. Measurements of supernova and baryon acoustic oscillations hint at subtle variations in dark energy's strength across cosmic epochs. Could these fluctuations be echoes of prior cycles, traces of a universe where dark energy did fade, collapsing everything before the reset? It's a tantalizing thread to pull. If dark energy isn't a fixed feature of reality but a dial that turns between cycles, its behavior could be the ultimate clue to whether we're trapped in a loop. Even stranger, dark energy might not act alone. Some theories propose it's entangled with dark matter, the two locked in a dance where one's dominance triggers the other's rise. In this scenario, the universe wouldn't just expand and contract, it would breathe, with dark energy and dark matter trading control like seasons. Each cycle could leave faint imprints in the cosmic microwave background or the large-scale structure of galaxies, subtle fingerprints waiting to be decoded. The stakes couldn't be higher. If dark energy is truly constant, our fate is a cold, empty void, a universe so stretched thin that not even atoms can hold together. But if it's dynamic, then the cosmos might be a phoenix, forever rising from its own ashes. The answer lies in the next generation of telescopes, like the Euclid satellite or the Vera Rubin Observatory, which could detect tiny changes in dark energy's push over billions of years. Until then, we're left with a haunting question. Is the universe racing toward oblivion or just pausing between verses of the same endless song? The multiverse concept shatters the idea of a single, linear cosmic cycle. What if every reboot doesn't just repeat history but branches it? Picture a tree growing rings. Each layer represents a new universe born from the collapse of the last, yet with countless diverging paths. This isn't just science fiction. String theory's ekpyrotic model paints a startling vision of reality as a series of colliding membranes, higher dimensional planes that periodically crash together, igniting new big bangs like cosmic symbols clashing in the dark. Each collision wouldn't just reset the universe, it could tweak the fundamental constants, spawning variations where gravity is stronger, light faster, or atoms unstable. Suddenly, the cosmic loop isn't a monotonous rerun but an infinite tapestry of possibilities. The math behind this is as elegant as it is mind-bending. In the ekpyrotic scenario, our three-dimensional universe exists on a brane, a slice of higher dimensional space floating like a leaf in a vast cosmic ocean. Nearby, other branes drift, parallel universes with their own physics, their own histories. When these branes collide, the energy of impact triggers a new cycle. But here's the twist. Quantum fluctuations during the collision could warp each new universe in unique ways. Imagine two sheets of paper smacking together. The wrinkles left behind aren't identical. Some regions might birth stars that burn colder, others might lack dark matter entirely. Over infinite cycles, this process wouldn't just replay the universe, it would remix it. But how would we know? If other branes exist, their gravitational pull might leave faint fingerprints in our cosmos, anomalies in the cosmic microwave background where spacetime itself bears stretch marks from ancient collisions. Some physicists even speculate that certain impossible particles detected in deep space observatories could be refugees from neighboring branes leaking through dimensional cracks. And if dark energy behaves differently in other cycles, its signature might linger like a shadow, detectable in the way distant supernova flicker. The implications rewrite the meaning of existence. In a branching multiverse, every choice you make, every chance encounter, every atom spin, might spawn alternate versions of reality where the dice rolled differently. Your life, your world, could be just one iteration in an infinite ensemble, each cycle subtly editing the script. It's a vision that blurs the line between science and metaphysics, where the cosmos isn't just eternal but endlessly inventive, exploring every possible version of itself across the expanse of eternity. Kurt Gödel, the revolutionary mathematician, shattered the illusion that we could explain everything when he proved that even in the most rigorous logical systems, some truths remain forever beyond our grasp. His incompleteness theorems revealed a humbling reality. No system of math complex enough to describe basic arithmetic can ever be both complete and consistent. There will always be statements that are true but unprovable, lurking just outside the reach of logic. Now, take that unsettling idea and stretch it across the cosmos. If our most precise language, mathematics, has inherent blind spots, what does that say about our ability to comprehend the universe's deepest secrets, like the cosmic loop? Think of it like a maze with no exit. Gödel showed that within any given system, you can construct questions the system itself can't answer. Apply that to cosmology, and suddenly, the cyclicity of the universe might not just be hard to prove, it could be fundamentally unprovable from within. We're like fish trying to describe water, trapped inside the very reality we're attempting to decode. Our tools might be insufficient to perceive the full pattern. Even if the universe is locked in an endless cycle, the evidence could be hiding in our logical blind spots, as unreachable as a shadow just beyond the light. This isn't just philosophical musing, it's a concrete paradox. To fully model a cyclical universe, we'd need a mathematical framework that encompasses all possible states of existence across infinite iterations. But Gödel's work suggests such a framework would inevitably generate truths it couldn't validate, like a cosmic version of the liar's paradox. Imagine a universe that declares, "This statement is false," in the next cycle. Could we ever test that, or consider the eerie alignment between Gödel's theorems and closed time-like curves, those twisted loops in space-time where cause and effect circle back on themselves? If time itself is cyclical, our logic might be just as trapped in the loop as matter and energy, forever chasing its own tail. Historically, every time we've hit the limits of understanding, we've invented new tools to push further. Newton's calculus unlocked celestial mechanics, Einstein's relativity warped our sense of space-time, and quantum theory forced us to embrace uncertainty. But Gödel's theorems hint that some walls won't fall, no matter how clever our math. The cosmic loop might be one of them, a truth as real as gravity, yet forever hovering just outside the provable. It's as if the universe coated itself with a firewall, shielding its ultimate nature from the very minds it spawned. Yet here's the twist: if the cosmos truly cycles, each iteration might tweak the rules just enough to let consciousness evolve new ways of seeing. Like a chess game where the board reshapes after every move, perhaps the loop isn't a prison but a classroom, giving intelligence infinite chances to solve the unsolvable. Or maybe, as Gödel feared, some mysteries are simply the universe's way of reminding us not all doors are meant to open. Consciousness might be the ultimate blind spot in the cosmic loop, the one thing that can't be neatly recycled. We assume time flows forward like a river, carrying us from birth to death in a straight line. But what if that's just a trick of perception? Physicist Julian Barber's radical, timeless physics suggests that time isn't a fundamental feature of reality, but an illusion stitched together by our brains. Picture a film strip where every frame exists simultaneously, and consciousness is just the projector's light creating the illusion of motion. In this view, the past, present, and future are all equally real, locked in an eternal now. Apply that to the cosmic loop, and suddenly the idea of repetition collapses. Every moment, every version of you isn't repeating but simply exists, stacked like pages in a book the universe keeps rereading. This reshapes how we think about eternal recurrence. Nietzsche's nightmare that we're doomed to relive identical lives forever might be missing the point. If time is an illusion, then the loop isn't a cycle but a constellation, with all iterations of reality shimmering at once. Your first kiss, your last breath, the heat-death of the universe, they're not sequels but simultaneous facets of a single, infinite structure. Even déjà vu takes on new weight, not a glitch but a fleeting glimpse of the underlying timelessness, like catching your reflection in a spinning disco ball. The unsettling question isn't whether consciousness survives the loop, it's whether it ever enters it. Some quantum consciousness theories propose that awareness isn't generated by the brain but harvested from deeper layers of reality, like a radio tuning into frequencies beyond space-time. In a cyclical cosmos, this could mean your sense of self isn't bound to one iteration but flickers across them all, stitching together a cohesive identity from fragments scattered across eternity. Imagine waking from a dream where you lived 1,000 lives, only to realize none were dreams, just different chapters of the same story read out of order. Yet here's the paradox: if time is an illusion, why does it feel so real? Evolution might hold the answer. Our brains didn't develop to perceive cosmic truths but to survive, to sequence events into cause and effect narratives that help us dodge predators and light fires. Linear time is a user interface, a simplified dashboard for navigating a reality far stranger than we can comprehend. Even physics bends to this bias. Entropy, the arrow of time, might just be a statistical tendency, not a law. Flip the cosmic coin enough times, and occasionally a universe appears where eggs unscramble and memories flow backward. Barber's timeless universe doesn't erase change, it redefines it. Think of a mountain seen from afar, static, unchanging, but climate and every step reveals new vistas. The mountain was always whole, only your perspective shifted. In the cosmic loop, every possible state of the universe exists eternally. What we call time is just the path our consciousness takes through the labyrinth. The loop isn't a prison but a gallery, and we're the visitors, mistaking the order of our footsteps for the layout of the rooms. So where does that leave us? If the cosmic loop is real, our struggle isn't against repetition but against the limits of perception. The universe might be singing the same song forever, but we're only hearing one note at a time. String theory whispers of a universe built not from particles but from tiny, vibrating filaments, threads of energy so small that if an atom were the size of a solar system, a string would be a tree on one of its planets. These loops and strands don't just sit idle, they dance, their oscillations determining everything from the mass of an electron to the gravitational pull of a black hole. Now take that idea and scale it up to the cosmic level. What if the same vibrations that define particles could also orchestrate the birth, death, and rebirth of universes? Hidden within the math lies a breathtaking possibility. The cyclical nature of existence might be written in the harmonies of these strings. Picture a guitar string plucked to produce a note. Change its tension and the pitch shifts. String theory suggests the cosmos operates similarly. The notes of vibrating strings define the laws of physics in our universe. But here's the twist. Some versions of the theory propose that the collapse of a universe could be like a string slipping to a lower frequency, resetting the cosmic tune. The Big Bang wouldn't be an absolute beginning but a transition, a moment when the vibrations of the previous universe reached a crescendo before settling into a new, stable pattern. It's as if reality itself is a symphony, with each movement ending in a grand finale that births the next. The stage for this drama isn't the three-dimensional space we know, but a hidden landscape of compacted dimensions, shapes so intricate they boggle the mind. Calabi-Yau manifolds, those six-dimensional geometric wonders curled into every point in space, could hold the key. Imagine a garden hose viewed from a distance. It looks like a simple line, but up close, it's a tube with a circular cross-section. Calabi-Yau spaces are like that, except with dimensions folded into knots and twists so complex they could encode entire universes worth of information. When a universe collapses, these shapes might reconfigure, their topology shifting like a Rubik's cube tumbling into a new arrangement. The result? A rebooted cosmos with slightly adjusted constants, where gravity is stronger here, light slower there, each cycle a variation on the same fundamental theme. Critics argue this sounds more like metaphysics than physics, but the equations don't lie. In string theory's framework, the energy required to collapse and rebirth a universe isn't infinite, just unimaginably large, concentrated at scales where quantum effects dominate gravity. Some models even suggest that the vacuum of space isn't truly empty but seething with potential, a quantum foam where bubbles of new universes can nucleate and inflate. If our cosmos is one such bubble, its death might spawn countless others, each with its own vibrational signature. The loop isn't just temporal but fractal, with universes nesting within universes like Russian dolls, all humming to the tune of their strings. Yet the most haunting implication isn't about mechanics, it's about memory. If string vibrations carry over between cycles, could traces of past universes linger in the resonant frequencies of particles today? Some theorists speculate that dark matter, that enigmatic substance outweighing normal matter 5-to-1, might be composed of relics from prior iterations particles whose strings vibrate at frequencies just beyond our detection. Even the Higgs field, which gives particles mass, could be an echo of a previous universe's final chord, frozen into the fabric of our own. The beauty of this idea lies in its audacity. String theory doesn't just offer a mechanism for cosmic rebirth. It turns the universe into a living, breathing entity, its rhythms dictated by the oldest music of all, the song of strings stretching across eternity. Whether the math will ever be testable remains an open question, but one thing's certain. If the cosmic loop is real, we're not just stardust, we're vibrations in an endless symphony, notes held for a moment before the universe takes a breath and begins again. Sir Roger Penrose, the Nobel Prize-winning physicist who reshaped our understanding of black holes, dared to ask an even deeper question. What if the universe's death isn't an end but a cosmic metamorphosis? His conformal cyclic cosmology proposes a vision so radical it bends the mind, a cosmos where time loses all meaning at the boundaries between cycles, and infinity becomes the bridge between one universe and the next. Unlike traditional Big Bang models, Penrose's theory suggests that when our universe expands into cold, empty oblivion, the very concept of scale dissolves. Distances stretch so vastly that all particles effectively occupy the same point, erasing any sense of size. At this moment of conformal rescaling, the dead husk of our universe becomes mathematically identical to the hot, dense singularity of a new Big Bang. The end literally transforms into a beginning, not through a violent collapse but a seamless reconfiguration of spacetime itself, the most startling part. Penrose claims we can see the echoes of past universes. He points to anomalous rings and patches in the cosmic microwave background, regions where temperatures fluctuate in concentric circles rather than random speckles. Dubbed Hawking points in honor of his late colleague Stephen Hawking, these features shouldn't exist in standard cosmology. But if black holes from a prior eon evaporated via Hawking radiation, their final bursts of energy might have left ghostly imprints on our newborn universe, like shadows cast through the veil of cosmic rebirth. It's as if the CMB isn't just a baby picture of our universe but a palimpsest, scribbled with faint memos from a reality that predates time. Critics argue these patterns could be statistical flukes, but Penrose's team has doubled down. Their analysis of data from the Planck satellite identifies rings with spacing and temperatures that align eerily with predictions, regions where the temperature variance is up to 10 times stronger than random chance would allow. Even stranger, these rings sometimes overlap, creating stacked signatures that resemble targets. If verified, it would mean our universe didn't just inherit raw energy from a predecessor but structured information, encoded in the geometry of spacetime itself. The philosophical implications are staggering. In Penrose's model, the laws of physics might not be arbitrary constants but evolutionary holdovers refined across countless cycles. Entropy, the arrow of time, resets with each eon, solving the Boltzmann brain paradox by ensuring each universe starts fresh yet carries forward subtle traces. Consciousness itself could be part of this continuum, not merely a byproduct of one universe's laws, but a thread woven through the fabric of eternity. Yet the theory isn't without cracks. Mainstream cosmologists note that conformal cyclic cosmology requires exotic physics, like massless particles dominating the universe's far future, a scenario with no experimental support. Others question whether Hawking points are truly unique. Simulations show some similar patterns can emerge from random quantum fluctuations, but Penrose counters that the precision of the ring spacing defies coincidence. The debate rages on, a reminder that even at the frontiers of physics, the line between brilliance and heresy is razor thin. What's undeniable is the theory's audacity. Penrose doesn't just suggest the universe repeats, he rewrites the rules of the loop, turning the cosmic cycle into an endless act of transformation where information, structure, and perhaps even meaning survive the furnace of infinity. If he's right, the night sky isn't just a window to the stars but a looking glass, reflecting universes we've forgotten and those we've yet to meet. Time crystals sound like something ripped from a sci-fi novel, but they're very real, and they might hold clues to the universe's deepest secrets. Unlike ordinary crystals, which arrange atoms in repeating patterns in space, time crystals repeat their structure in time, flipping between configurations like a cosmic metronome without any energy input. Normal matter settles into equilibrium, but these bizarre phases of matter never do. They're the first known examples of non-equilibrium matter, dancing to a rhythm all their own. The implications are staggering. If tiny structures can oscillate eternally without energy loss, could the cosmos itself be locked in a similar, unending dance? The discovery of time crystals in 2016 sent shockwaves through physics. Imagine a ring of atoms that, when nudged, doesn't just settle into a stable state but keeps cycling between two configurations indefinitely, resisting entropy's pull. It's like a pendulum that swings forever without friction, a violation of classical physics that's only possible thanks to quantum weirdness. What makes them even stranger is their relationship with symmetry. Normal crystals break spatial symmetry. Their repeating patterns don't look the same in every direction. Time crystals break time symmetry, their atomic choreography out of sync with the forces driving them. They don't just exist in time, they rewrite its rules. Now, stretch that idea to cosmic scales. If microscopic systems can exhibit eternal motion, why not the universe itself? Some theorists speculate that time crystals could be a hint, a fractal echo of a deeper truth about reality's cyclical nature. The cosmic microwave background's faint temperature variations, the large-scale structure of galaxies, even the mysterious synchronization of black hole mergers, all might be shadows of a universe that's not just looping but pulsing, its very fabric oscillating across epochs. But here's where it gets wilder. Time crystals don't just repeat, they remember. Their oscillations can encode quantum information, resisting disturbances that would scramble ordinary matter. This resilience mirrors theories about black holes preserving data across cosmic cycles, or quantum entanglement threading one universe's remnants into the next. Could time crystals be the universe's way of ensuring certain patterns survive its death and rebirth, a cosmic backup drive etched into the bones of reality? Skeptics argue that scaling up from lab-grown time crystals to an entire universe is a leap too far. Yet the underlying principle, that matter can defy equilibrium, that time itself might have a hidden granularity, challenges our assumptions about how reality must behave. If tiny diamonds doped with nitrogen can pulse in perpetuity, who's to say space-time doesn't harbor similar rhythms on scales we've yet to fathom? The most haunting possibility isn't just repetition but resonance. Like a struck tuning fork, the universe might vibrate at frequencies we're only beginning to detect. Time crystals could be the first note in a symphony we've been deaf to, a symphony where the music never ends because the composer is time itself. The second law of thermodynamics seems like the ultimate party pooper. It declares that entropy, the universe's tendency toward disorder, must always increase. In plain terms, everything is destined to wind down like a clock ticking toward stillness. Stars will burn out, black holes will evaporate, and eventually the cosmos will reach a state of maximum entropy, a lukewarm, featureless void where nothing happens forever. This grim fate is called heat death, and it appears to slam the door shut on any cosmic loop. If entropy only grows, how could the universe possibly reset itself for another cycle? The answer might lie in the quantum underworld, where the rules we take for granted start to crumble. Enter quantum resurrection. At scales smaller than atoms, particles routinely defy classical logic, popping in and out of existence or tunneling through barriers that should be impenetrable. Some physicists, like Sean Carroll, suggest that given enough time, think numbers so large they dwarf the age of our universe, quantum fluctuations could spontaneously reorganize the void. Picture a cup of coffee cooling to room temperature. Thermodynamics says it won't suddenly heat up again unless you wait longer than eternity. Then, statistically, all the molecules might just jiggle back into a steaming mug. Apply that to the cosmos, and even after heat death, quantum randomness could, against all odds, birth a new Big Bang from the ashes of the old. It's like the universe playing a game of chance with infinite rolls of the dice. Eventually, it hits cosmic jackpot. But there's another twist. What if entropy doesn't carry over between cycles? Roger Penrose's conformal cyclic cosmology proposes that at the end of time, when the universe stretches into an ultra-smooth, cold expanse, the very concept of distance becomes meaningless. In this state, the universe's gargantuan size and its collapsed beginning become mathematically identical. Entropy resets not because it's reversed, but because scale itself dissolves. It's not a rewind, but a recalibration, where the universe's clock zeroes out without ever violating thermodynamics. Think of it like an artist erasing a canvas so thoroughly that the next painting isn't a copy. It's a fresh start with no memory of the strokes that came before. Critics argue these ideas flirt with metaphysics, and they're not wrong. The math behind quantum resurrection relies on probabilities so slim they might as well be zero for all practical purposes. And Penrose's model requires conditions so extreme they're untestable with current technology. But here's the kicker: heat death assumes the universe is a closed system with no external influences. If we're part of a multiverse where our cosmos is one bubble in a froth of others, energy or information could bleed in from neighboring realities, offering a loophole. Imagine a room where the air slowly settles to stillness, but someone outside keeps cracking the window. The second law holds inside, but the larger system. All bets are off. The most haunting possibility isn't that entropy dooms the loop, it's that entropy might enable it. Recent work in black hole thermodynamics suggests that maximum entropy isn't the bland state we assumed. Instead, it could be a hive of quantum activity where spacetime churns with latent structure, like a frozen lake that seems lifeless until you spot the fish moving beneath the ice. A dead universe might seethe with potential, waiting for the right trigger to reboot. Whether through quantum luck, higher dimensional leaks, or the universe's own hidden resilience, the loop might not defy the laws of physics. It could be the ultimate expression of them. After all, if time itself is cyclical, who's to say entropy isn't just another verse in the song? Cosmic inflation didn't just jumpstart our universe. It might have set the stage for an infinite multiverse where every bubble reality dances to its own rhythm. Picture a pot of water boiling violently, with bubbles forming, expanding, and drifting apart, each encapsulating its own pocket of steam. Now scale that up to the fabric of spacetime itself. Alan Gough's groundbreaking work in the early 1980s revealed that the universe underwent a mind-boggling exponential expansion in the first fraction of a second after the Big Bang. But here's the kicker: inflation might not have stopped everywhere. In some regions, it could still be happening, endlessly spawning new universes like bubbles in an infinite cosmic froth. Each of these bubbles would cool into its own distinct reality, with its own laws of physics, its own arrow of time, and possibly its own version of the cosmic loop. This isn't just speculation. The math paints a vivid picture. Eternal inflation suggests that when one patch of spacetime stops inflating and settles into a stable universe, the surrounding space keeps expanding at breakneck speeds, carrying other budding universes out of reach. It's like lighting fireworks in a hurricane. Some explode nearby, while others are whisked away before you even see them ignite. These disconnected bubble universes could each follow their own fate. Some might collapse and rebound in cycles, others might stretch into cold oblivion, and still others could spawn life in forms we can't even fathom. The terrifying beauty of this idea: our entire observable cosmos, with its hundreds of billions of galaxies, might just be a single bubble in an endless sea of inflating spacetime. Gough's theory doesn't just multiply universes, it shatters the idea of a single, linear timeline. If inflation is eternal, then time itself becomes a local phenomenon, relevant only within each bubble. One universe's Big Bang could be another's Tuesday, and if some of these bubbles are cyclical, their resets wouldn't sync up any more than the tides of distant oceans. Imagine two pocket watches ticking in separate rooms. One might chime midnight while the other reads noon, yet both keep perfect time within their own walls. The multiverse wouldn't just contain loops, it'd be a symphony of them, each playing in a different key. But how would we ever know? If other bubble universes exist beyond our cosmic horizon, their light will never reach us. The same inflationary expansion that birthed them also exiled them forever. Yet subtle clues might linger in our own backyard. Some models suggest that collisions between adjacent bubbles could leave bruises in the cosmic microwave background, anomalous temperature patterns, or circular distortions that defy conventional explanations. It's like finding a fingerprint on a window pane, evidence of something pressing in from the other side. Another tantalizing hint comes from dark energy's behavior. If its strength varies across bubbles, our universe's particular value might be a fluke, one possible setting in a vast multiversal menu. The implications rewrite the meaning of existence. If eternal inflation is real, then the cosmic loop isn't just a feature of our universe, it's one variation in an infinite ensemble. Some bubbles might recycle endlessly, their histories repeating like scratched records. Others could spiral into novelty, their physical constants tweak just enough to break the cycle. And somewhere out there, in the unobservable vastness, another version of you might be pondering the same questions in a universe almost, but not quite, the same as this one. The multiverse doesn't dilute the mystery of the loop. It magnifies it, turning the cosmos into a kaleidoscope where every twist reveals another reflection of time's strange dance. Neutrinos are the universe's ultimate shape-shifters, particles so elusive they pass through a light year of lead without a single collision. But their strangest trick isn't just slipping through matter, it's their ability to transform identities mid-flight. One moment they're electron neutrinos, the next tau or muon neutrinos, dancing between flavors like cosmic chameleons. This phenomenon, called neutrino oscillation, defies classical physics. If these ghostly particles can carry secrets across light years, could they also ferry messages between universes? The math behind neutrino oscillations is eerily elegant. As these particles zip through space at nearly the speed of light, their quantum states evolve, governed by subtle differences in mass and energy. It's as if each neutrino is a locked briefcase, and the journey itself twists the dials until the code clicks open, revealing new content. Now imagine that journey stretching not just across galaxies but across cosmic cycles. If information survives the death of one universe, encoded in quantum fields or space-time geometry, neutrinos might be the perfect couriers, slipping through the chaos of a big crunch to deliver data to the next iteration. Some theorists take this further. Neutrinos interact so weakly with ordinary matter that they're practically immune to entropy's erasure. While stars explode and black holes evaporate, these phantoms could persist, carrying imprints of prior universes like microscopic time capsules. The idea isn't as far-fetched as it sounds. Experiments like IceCube have already detected high-energy neutrinos from distant galactic cataclysms, particles that traveled billions of years undisturbed. If they can cross those distances unscathed, why not the gulf between cosmic eons? The real shock comes when you consider their potential encoding mechanisms. Neutrino oscillations depend on three mixing angles and a phase parameters that, if tweaked even slightly, would alter their behavior dramatically. What if these values aren't arbitrary but fine-tuned from cycle to cycle? Like a cosmic enigma machine, neutrinos might shuffle their properties in patterns that only make sense when read against the backdrop of multiple universes. A team at CERN even proposed that hypothetical sterile neutrinos, ghosts within ghosts, could act as conduits between dimensions, their oscillations branching into realities we can't perceive. Skeptics argue this veers into metaphysics, and they're not entirely wrong. No experiment has yet proven neutrinos can outlast the universe's death. But consider this, when the last black hole evaporates and the cosmos goes dark, neutrinos will still outnumber atoms by 1 billion to 1. They'll be the final witnesses, the last flickers of structure in a sea of entropy. If anything can whisper secrets across the void, it's these spectral messengers, threads stitching the tapestry of existence cycle after cycle. The most haunting possibility, we might already have their messages, the cosmic neutrino background, a faint relic from just 1 second after the Big Bang, bathes the universe in whispers we're only now learning to hear. Deep inside detectors buried under mountains of ice or submerged in Mediterranean waters, physicists hunt for anomalies, patterns that don't fit the standard model. A single deviation, a blip in the oscillation data, could be the first syllable of a story older than time. So the next time you feel sunlight on your skin, remember, trillions of neutrinos are passing through you every second, untouched and uncharted. Most are noise, but somewhere in that flood there might be a signal, a letter from a universe we've forgotten, waiting for us to decode its handwriting. Imagine an AI so advanced it could sift through the raw data of the cosmos like a detective combing through decades of cold case files. Machine learning is already transforming astronomy. Deep neural networks identify distant galaxies faster than human eyes. Algorithms predict supernova before they flare into view. But what if we train these systems to hunt for something far stranger? The fingerprints of a universe stuck on repeat. The answer might lie in the avalanche of data flooding in from sky surveys, gravitational wave detectors, and cosmic microwave experiments, datasets so vast and complex that only artificial intelligence could spot the subtle echoes hidden within. Take the cosmic microwave background. Tiny temperature variations in this primordial light form intricate patterns like a cosmic fingerprint. To human analysts, these patterns appear random, but an AI trained on simulations of cyclical universes might recognize deviations from the expected noise, anomalies that align with predictions of prior collisions or quantum imprints from a previous cycle. Researchers at Perimeter Institute have already used machine learning to map the CMB in ways that reveal hidden structures, uncovering asymmetries that defy standard inflationary models. Pair this with AI trained to detect repeating statistical signatures like concentric rings or spiral distortions, and we might stumble upon evidence that the universe has done this all before. But the real game changer could be black hole mergers. Every time two black holes spiral into each other, they ring spacetime like a bell, emitting gravitational waves with unique frequencies. AI systems monitoring these events might notice something eerie. Mergers whose waveforms match predictions from ancient cycles. In a looped cosmos, black holes from prior iterations could leave gravitational ghosts, subtle harmonics in the data that recur like motifs in a symphony. Advanced algorithms like those used in LEGO are already spotting mergers once invisible to traditional methods. What if the next breakthrough isn't a new detection but a recognition? A signal that mathematically aligns with collisions from a universe that predates our own. The challenge is teaching AI to ask the right questions. Current machine learning excels at finding what we tell it to seek, but uncovering evidence of cosmic loops requires a leap into the unknown. That's where unsupervised learning comes in. By feeding raw cosmological data into self-organizing neural networks, systems designed to find patterns without human bias, we might stumble on correlations no theorist ever imagined. Imagine an AI clustering galaxy rotations into groups that shouldn't exist under standard models or flagging quantum vacuum fluctuations that sink across billions of light years. These anomalies could be glitches or they could be breadcrumbs leading back to a cycle we've yet to comprehend. Even more provocative is the idea of AI as a time capsule. If civilizations in prior cycles reached similar technological heights, they might have encoded messages in constants of nature or quantum states, a cosmic SOS meant to outlast universal rebirth. Machine learning could be the key to decoding such signals, scanning mathematical constants for non-random patterns or analyzing particle behavior for unnatural symmetries. The very algorithms we're building today might one day crack a cipher older than time, revealing that the loop isn't just a theory but a legacy, passed down through the collapse and rebirth of reality itself. Of course, skepticism is healthy. AI is only as good as the data and parameters we feed it, and pareidolia. the tendency to find patterns in randomness affects machines as much as humans. But as neural networks grow more sophisticated, their ability to distinguish true signals from noise could surpass our own. The day an AI points to a dataset and declares with calculable certainty, "This structure shouldn't exist unless the universe has cycled before," might be the day we confront a truth as humbling as it is electrifying. Until then, we're left with a tantalizing thought. The ultimate proof of the cosmic loop may not be written in the stars, but in the ones and zeros of the machines learning to read them. Friedrich Nietzsche's concept of eternal return isn't just a thought experiment, it's a sledgehammer to the soul. What if every choice you've ever made, every joy and every agony, is destined to replay in an infinite loop with no variation, no escape? The German philosopher framed this as the ultimate test of one's love for existence. Would you live the same life again and again for eternity? For some, the idea is liberating, a cosmic stamp of approval that every moment, no matter how trivial, carries eternal weight. For others, it's a prison sentence, stripping life of novelty and reducing humans striving to a script written in the stars. This tension between meaning and despair hinges on a single question: does repetition amplify significance or erase it? Ancient Stoics might argue that cyclical time dignifies suffering. If pain is inevitable, its recurrence makes endurance heroic rather than futile. But modern existentialists like Jean-Paul Sartre recoiled at the idea, insisting that meaning springs from our freedom to choose, not from predestined reruns. If the universe is stuck on repeat, does courage lose its edge, or does it become the only sane response to an indifferent cosmos? The paradox cuts deeper. If every detail recurs identically, then even your rebellion against the loop was preordained, a twist that bends free will into a mirage. Yet quantum mechanics might offer a loophole. At microscopic scales, particles behave unpredictably, their actions governed by probability, not certainty. Scale this up to cosmic cycles, and tiny quantum variations could introduce enough randomness to break the chain of identical repetition. Suddenly, Nietzsche's nightmare becomes a kaleidoscope, each cycle similar but never the same, like jazz improvisations on a timeless melody. But here's the wrenching beauty of eternal return. It forces us to confront what we truly value. If your life were a museum exhibit, revisited endlessly by future versions of yourself, would you curate it differently? The idea reframes regret as a kind of temporal vertigo. Not just sorrow for what was, but dread of what will always be. Yet it also offers a perverse comfort. In a universe where nothing is lost, every act echoes forever. Your kindness to a stranger, your quiet moments of creativity, even your failures, none of it vanishes. They're etched into the fabric of reality, as permanent as the stars. The debate spills beyond philosophy into physics. If Penrose's conformal cyclic cosmology is correct and information survives between universes, then Nietzsche's poetic vision might have a mathematical backbone. Consciousness itself could be part of this continuity, with each iteration of the universe refining its capacity for awareness. We're not just replaying history, we're rehearsing it, inching toward some unknown crescendo. Or perhaps the loop is a mirror, forcing us to stare into the abyss until we finally recognize our own reflection. Whether the cosmic loop is a curse or a covenant depends on where you stand. For the artist, it's a challenge: create something worth repeating. For the lover, it's a vow every embrace is infinite. And for the scientist, it's a riddle wrapped in the night sky, whispering that the universe might not just endure but remember. The terror of eternal return isn't that we'll live the same life forever. It's that we might finally have to ask ourselves, was it enough? Wormholes aren't just sci-fi plot devices, they're legitimate solutions to Einstein's equations, theoretical tunnels through space-time that could, in principle, connect distant moments or even universes. If the cosmic loop is real, could these cosmic shortcuts offer an exit? The math suggests it's not impossible. A stable wormhole would require exotic matter with negative energy to prop it open, something we've glimpsed in fleeting quantum experiments. Picture threading a needle through the folds of a collapsing universe, stitching a bridge to the next cycle before the crash. Even more radical, if black holes birth new universes inside their singularities, as loop quantum gravity proposes, conscious beings might engineer a controlled descent, swan diving into oblivion to emerge somewhere new, like cosmic seeds carried by gravity's tide. But escape isn't just about physics, it's about memory. If consciousness is the universe's way of observing itself, could self-awareness be the key to breaking the loop? Eastern philosophies have long argued that enlightenment, a state of pure, timeless awareness, transcends cyclical existence. Modern theorists like Donald Hoffman take this further, suggesting reality itself might be a user interface, a simplified projection of deeper, timeless structures. In this view, breaking the loop wouldn't require manipulating space-time but perceiving beyond it, like waking from a recurring dream by realizing you're the dreamer. Then there's quantum suicide, a thought experiment so chilling it borders on myth. Imagine a device linked to a quantum particle's random decay. If the particle decays, the device kills you. If not, you survive. In a multiverse where every possibility branches, you'd only experience timelines where you keep surviving, no matter how improbable. Scale this up to cosmic cycles, and a civilization might rig their universe's collapse to trigger survival in a lone, escaping bubble, a Hail Mary played across infinity. Of course, this is metaphysical speculation, but it underscores a haunting question. In an eternal loop, is survival a fluke or a forced move, the darkest twist? The loop might not need breaking, if each cycle isn't a perfect copy but a variation like dice tossed with slightly different weights, then novelty survives. Consciousness, technology, even art could accumulate across iterations, refining toward some unknown zenith. The exit isn't a door but an evolution, a slow awakening where the universe, through us, learns to rewrite its own rules. Until then, we're left with a paradox. The only way to escape the loop might be to embrace it so fully that we outgrow it. The evidence is mounting not in neat lines, but in echoes, anomalies, and whispers from the edges of reality. The cold spot in the cosmic microwave background, those concentric rings in the radiation that Penrose insists are scars from a universe before ours. The eerie synchrony of black hole mergers, their gravitational waves tolling like bells across the void, as if rehearsing a rhythm older than time itself. Even the laws of physics seem suspiciously fine-tuned, as though calibrated by trial and error across countless iterations. And then there are the myths, the Hindu Wheel of Time, the Norse Ragnarok, the Aztec Fifth Sun, all singing the same refrain: destruction is never the end, just the pivot before rebirth. But here's the thought that lingers long after the equations fade and the stories settle. If the universe truly loops, then this moment, your breath, the screen's glow, the weight of the question hanging between us has already happened. Infinite times before, infinite times to come. Are we actors in a script we can't remember, or is the cosmos more inventive, weaving variations into each cycle like a jazz musician riffing on an old standard? The answer might be written in the quantum flicker of a neutrino, the spin of a time crystal, or the silent collapse of a black hole we'll never see. Until then, we're left with the awe and the ache of not knowing. So what do you think? Is reality a record stuck on repeat, or a symphony with movements we've yet to hear? Drop your wildest theories in the comments, and if this journey through the cosmic loop left you questioning everything, hit subscribe. The universe might be cyclical, but the next mind-bending revelation. That's just one click away.